Hi, and welcome to this Now Maths video on writing recurring decimals as fractions. This video will be great for you if you're just getting started with recurring decimals. As always, you can click through the chapters if you're only interested in specific parts of this topic. You can also check out our Revise Now video if you want a shorter recap. So starting off with the basics, what are recurring decimals? A decimal recurs if it goes on forever in a specific pattern. So an example of a recurring decimal might be something like 0.3333, where the 3 repeats infinitely. This is 0.3 recurring. Or another example might be something like 0.572, 572, 572, and so on, with that pattern repeating infinitely. In maths, the notation we use for recurring decimals is a dot above the number or pattern that repeats. So for 0.3 recurring, we would write 0.3 with a little dot above the 3 to show that it goes on infinitely. And for the 0.572 recurring, we would put 0.572 and we would put a dot above the 5 and the 2 to show that everything between the 5 and the 2 is repeated infinitely. So which of these decimals are recurring? So starting with 0.5, 0.5 is what we call a terminating decimal. There's no repetition or any dot to signify any repetition, so this is not recurring. The next decimal we have is 0.3333, and we have 3 little dots afterwards. This shows us that this decimal does in fact continue infinitely in this pattern, and usually we would write this as 0.3 with a little dot above the 3 for 0.3 recurring. So this one is a recurring decimal. For our next decimal, we have 0.43 and we have the little recurring dot above the 3. So this is definitely a recurring decimal. And because the dot is only above the second digit after the decimal point, it is only that digit that repeats. So this decimal would look like 0.4333. And again, this goes on infinitely. Our next decimal is 0.25, and we have 2 recurring dots this time, so this is definitely a recurring decimal, and because there is a dot above the 2 and the 5, this tells us that the 2 and the 5 repeat infinitely, so we would have 0.25, 25, 25, and so on. For our next decimal, we have 0.6555. So this kind of looks like a recurring decimal because the 5 definitely repeats. However, there's nothing to tell us that this 5 goes on infinitely. There aren't any dots after the last 5 and there aren't any dots above any of the digits. So we can't say for sure that this is a recurring decimal, so we will say that it is a terminating decimal. And for our final decimal, we have 0.642 with recurring dots above the 6 and the 2. So this is definitely a recurring decimal, and the pattern repeats between the digits with dots above them. So we have 0.642, 642, 642, and so on. There are some common recurring decimals that you might already be able to write as fractions. For example, 0.3 recurring is 1/3, and 0.6 recurring is double this, so it's 2/3. Some slightly less common recurring decimals that you might already know are on screen now. If you aren't familiar with these decimals, hopefully you will be by the end of this video. So 0.1 recurring is equivalent to 1/9. 0.2 recurring is 2/9. 0.4 recurring is 4/9. 0.5 recurring, 5/9. 0.7 recurring, 7/9, and 0.8 recurring is 8/9. We're going to start off by showing how to prove results just like this. So let's start by using algebra to show that 0.6 recurring can be written as 2/3. All the questions we'll answer today will use the same algebraic method, and the working is extremely important for questions like these. We're going to start by labelling the decimal 0.6 recurring as x, and in maths we're going to write that we're going to let x equal 0.6 recurring. The point of doing this is that we're going to show that x can be written as a fraction that should be 2/3. For the purposes of this question, I'm actually going to rewrite this as x equals 0.666, and I'm going to put a few dots after to show that this is in fact a recurring decimal. Now if we're going to write x as a fraction, we need to try and eliminate the decimal, and we're going to do this by multiplying by 10. And if we start off by multiplying x by 10, we get 10x, and if we multiply 0.6 recurring by 10, we get 6.6 recurring because all of the digits shift to the left one place. Now if we look at the decimals that we're left with, if we were to subtract the smaller away from the larger, the 0.6 recurring part would completely cancel out, so we would be left with an integer, a whole number. So we're going to do exactly that, and to subtract them, I'm actually going to swap the order of them. So I'm going to write the 10x first, which we said was 6.6 recurring, and then I'm going to write the x second, which was 0.6 recurring. And then I'm going to set it up as a subtraction. And if we subtract these terms in turn, 10x subtract 1x is 9x. And then 6.6 recurring subtract 0.6 recurring would give us just 6, because the 0.6 recurring part would completely cancel. Now we're left with 9x equals 6. We're going to solve this to work out what x is, and we solve by dividing by 9. When we do this, we have x on the left, and then we could either calculate 6 divided by 9, or, for the purposes of this, 6 divided by 9 is the same as 6 over 9. Originally, we labelled 0.6 recurring as x, and we've ended up with 6/9 being x, which tells us that actually 0.6 recurring must be the same thing as 6/9. The question asks us to show that 0.6 recurring can be written as 2/3, and actually if we look at 6/9, we can simplify 6/9 by dividing by 3, and 6 divided by 3 is 2, 9 divided by 3 is 3, so 6/9 is the same as 2/3, which is the same as 0.6 recurring. So we've now showed that 0.6 recurring can be written as 2/3. Let's have a look at another one of our common recurring decimals. So this time we have to use algebra to write 0.8 recurring as a fraction. Even if you already know what 0.8 recurring is as a fraction, if asked to use algebra, we must show full working out to prove the result. So we will start by letting x equal 0.8 recurring. And similar to last time, I'm actually going to rewrite this as x equals 0.888, and I'm going to put 3 dots after to show that it goes on forever. Now we want to try and eliminate the decimal part of x. So I'm going to multiply x by 10 to give us 10x, and 0.8 recurring multiplied by 10 is 8.8 recurring because all of the digits shift to the left. Now, similar to what we did last time, we're going to subtract the smaller recurring decimal away from the larger, because that will cancel the decimal out, leaving us with something we can turn into a fraction. So I'm going to swap the order of these two recurring decimals. Now we've swapped them over, we're going to set this up as a subtraction. And then when we work out 10x, subtract 1x, we get 9x. And then we're going to subtract 0.8 recurring from 8.8 recurring. Similar to last time, the 0.8 recurring part cancels, and we are just left with 8. Now if we have 9x equals 8, to solve this, we're going to divide by 9. And when we divide 8 by 9, we're going to get 8 over 9, or 8/9. Since we started this question by calling x 0.8 recurring, and we've now found that x is actually 8/9, that tells us that 0.8 recurring must be equal to 8/9. 8/9 can't be simplified, and the question doesn't ask us to simplify either, so 8/9 is our answer. Now you've seen a couple of questions, you might want to grab a pen and see if you can use algebra to write 0.7 recurring as a fraction. Remember, showing all the steps is really important in questions like these. When you're ready to see a solution, press play. If you paused, welcome back. Let's see if our solutions match. So first we let x equal 0.7 recurring. You might have then chosen to write this as 0.777 with some dots after to show it goes on forever. We then multiply x by 10 to get 10x, and we multiply 0.7 recurring by 10 to give us 7.7 recurring. Now we swap them over and subtract. Subtracting x from 10x gives us 9x, and then subtracting 0.7 recurring from 7.7 recurring, the recurring part cancels, and 7 subtract 0 gives us just 7. So we're left with 9x equals 7, which we then solve by dividing by 9. So we end up with x equals, and 7 divided by 9 we write as 7/9. So given that we started by saying x is 0.7 recurring and we've ended with x equals 7/9, that tells us that 0.7 recurring must equal 7/9. And 7/9 can't be simplified, so that's our answer. Now we're going to look at some more complex recurring decimals and how to turn them into fractions. So in this question we're asked to use algebra again, so the method we'll use is the same as the previous question and relies on us eliminating the recurring decimal. So for this question we'll start in the exact same way and we will let x equal 0.72 recurring. And similar to previously, I'm going to rewrite this, and since there is a dot above the 7 and the 2, this decimal is 0.727272, and so on. Now we're going to multiply x by 10. So x multiplied by 10 is 10x, and 0.72 recurring multiplied by 10 gives us 7.2727, and so on, because all of the digits shift over to the left. If we now compare the decimal part of x and the decimal part of 10x, they don't quite match up because x has 7.27272 and 10x goes 272727. So what we're going to do is we're going to multiply by 10 again. And when we multiply 10x by 10, we get 100x. And when we multiply 7.27 recurring by 10, we get 72.7272, and so on. Now if we take a look at the decimal part of x and 100x, the decimal parts match up perfectly because they both go 727272 and so on. So if we subtract the first decimal from the third decimal, we're going to end up with a whole number or an integer. So let's set up a subtraction so that we can do that. So we'll have 100x on top, which is our 72.72 recurring, and we'll have x on the bottom, which is 0.72 recurring, and we're going to subtract. So starting off with 100x, subtract 1x, which gives us 99x. And then when we subtract the decimals, the recurring part will cancel, and 72 subtract 0 is just 72. Now we have an equation, 99x equals 72, and to solve this equation, we're going to divide by 99. So we end up with x equals, and 72 divided by 99 we can write as 72 over 99. So we can say that 0.72 recurring is equal to 72 over 99. The question asks us to write 0.72 recurring as a fraction in its simplest form. So let's see if we can simplify the fraction we've got. If we look at 72 over 99, 9 is a factor of both 72 and 99, so let's divide by 9. And 72 divided by 9 is 8, and 99 divided by 9 is 11. 8 and 11 don't share any factors, so our final fraction is 8/11. Now we're going to have a look at another similar question. So this time we're asked to use algebra to show that 0.213 recurring can be written as 71 over 333. To do this, we're going to ignore the fraction that we've been given in the question, and we're just going to focus on turning the recurring decimal into a fraction. And hopefully what we end up with should be the fraction that we are given in the question. So we're going to start off by letting x equal 0.213 recurring, and the dots are above the 2 and the 3, so it means that the digits between the 2 and the 3 repeat themselves. So we could write this as x equals 0.213, 213, 213, and so on. We're then going to multiply this by 10. And if we multiply x by 10, we get 10x. And if we multiply 0.213 recurring by 10, all the digits shift to the left, so we get 2.13, 213, 213, and so on. Looking at the two decimals we have, the recurring part doesn't match completely after the decimal point. This means we're going to multiply by 10 again. So if we multiply 10x by 10, we get 100x. And if we multiply 2.132 recurring by 10, we get 21.321321, and so on. Again, looking at the decimals we have, none of these decimals match completely after the decimal point. That means we're going to have to multiply by 10 again this time. So 100x multiplied by 10 is 1000x. And 21.321 recurring multiplied by 10 is 213.213, 213, 213, and so on. Now if we look again at the decimals, we can see that we have two that match perfectly after the decimal point. So the first decimal, 0.213 recurring, matches perfectly after the point with 1000x, which was 213.213 recurring. So we're going to subtract one decimal from the other in order to eliminate the recurring part. So I've set up our subtraction, so we're going to start off by doing 1000x subtract x, which is 999x. And then subtracting the decimals, we can see that the recurring part will cancel, and 213 subtract 0 is 213. Now we're left with the equation 999x equals 213. So to solve this, we divide by 999, which then gives us x on the left. And dividing 213 by 999, we get 213 over 999. So the recurring decimal we started with, which was 0.213 recurring, is equal to 213 over 999. The question asks us to show that it can be written as 71 over 333. Taking a look at what we have and what the question's given us, I can see that the denominator of the fraction we were given is a third of the denominator that we have. So let's see what happens when we divide by 3. If we divide 213 by 3, we do in fact get 71. So we have shown that 0.213 recurring can be written as 71 over 333. Now you've seen a couple of examples like this, you might want to pause the video here and see if you can use an algebraic method to write each of the recurring decimals as a fraction. If you pause the video, welcome back. Let's take a look at some solutions. So for our first question, we are writing 0.542 recurring as a fraction. So our first step is to let x equal 0.542 recurring. And you may have chosen to write this as 0.542, 542, and so on. Now for this question, I'm actually going to use a little trick that might help us out. Because there are 3 digits directly after the decimal point that are recurring, I know that in order to obtain another decimal that looks exactly the same after the decimal point, we need to shift this decimal 3 places over to the left. In order to shift the decimal 3 places over to the left, that means multiplying by 1000. So if I multiply x by 1000, I'll get 1000x. And if we multiply 0.542 recurring by 1000, the digits shift 3 places over, so we get 542.542, 542, and so on. Now straight away we've obtained 2 decimals where they both look completely identical after the point. Of course, you could have found 10x and 100x in between those 2 steps and you would get the exact same answer. Now let's subtract. So 1000x subtract x gives us 999x. And subtracting the decimals, we can see that the recurring part will cancel completely, and 542 subtract 0 is 542. Now we're left with 999x equals 542. So we can solve by dividing by 999 to give us an answer of x equals 542 over 999. This fraction doesn't actually simplify, and the question doesn't ask us to simplify, so we don't need to worry about it anyway. For our second question, we start in exactly the same way. So we let x equal 0.21 recurring. And again, you might have chosen to write this as 0.21, 21, and so on. This time, if we want to use our little shortcut, we can see that there are 2 digits directly after the decimal point that repeat themselves. So if we want to find a decimal that we can subtract this from and eliminate the recurring decimal, then we need to move this decimal 2 places over to the left. In order to move something 2 places to the left, we have to multiply by 100. So x multiplied by 100 is 100x. And if we multiply the decimal by 100, everything shifts over 2 places, so we end up with 21.2121 and so on. And we can see straight away that we have 2 decimals that match perfectly after the decimal point. Of course, if you decided to multiply by 10x in between these 2 steps, that is absolutely fine and you would get the same answer. Either way, we now need to subtract x from 100x. Now we've got our subtraction set up, we're going to do 100x subtract x, which is 99x. And then subtracting the decimals, we can see that the recurring part will cancel, and 21 subtract 0 is 21. Then we're left with 99x equals 21, so we can divide by 99 to give us that x equals 21 over 99. So we have our fraction. This time it asks for a fully simplified fraction, so looking at 21/99ths, I can see that 21 and 99 have a common factor of 3. So let's divide by 3 and see what we get. If we divide 21 by 3, we get 7. And if we divide 99 by 3, we get 33. And since 7 is prime and 7 doesn't go into 33, 7 over 33 is our final fraction. Fantastic work if you paused the video there and managed to get those answers correct. For our next question, we're asked again to use an algebraic method to write 0.53 recurring as a fully simplified fraction. The difference with this recurring decimal is that we can see that it is just the 3 that recurs, not both the 5 and the 3. We're still going to start this question in the exact same manner and we'll see what happens. So we'll start off by letting x equal 0.53 recurring. And if we were to write this out a little more fully, we could write this as x equals 0.5333 and so on. Now our aim is to find two decimals which match completely after the decimal point. So let's start by multiplying this by 10. So x multiplied by 10 is 10x, and if we multiply the decimal by 10, the digits shift over to the left to give us 5.3333 and so on. The two decimals we have here do not match perfectly after the point, so let's multiply by 10 again. So 10x multiplied by 10 is 100x, and 5.3 recurring multiplied by 10 is going to give us 53.33 and so on. Now looking at the three decimals that we have, we can see that two of them do in fact match after the point, and this time it's the 10x and the 100x which both end in 0.3 recurring. So this time we're going to subtract the 10x from the 100x. So working out our subtraction, this time we have 100x subtract 10x. That leaves us with 90x. Then here's the part where we need to be really careful because we're going to subtract these decimals, and similar to the previous questions, the recurring part completely cancels out. However, this time we are left with 53 subtract 5, which is 48. Now we're left with 90x equals 48, so we solve by dividing by 90. And that should give us x on the left, and 48 divided by 90 is 48 over 90. So our fraction is 48 90ths, and we can say that 0.53 recurring equals 48 90ths. Finally, the question does ask for us to make sure that our fraction is fully simplified, so let's just check. I can see that 48 and 90 are both even numbers, so they are definitely divisible by 2. So let's divide by 2 and see what we end up with. 48 divided by 2 is 24, and 90 divided by 2 is 45. Now checking 24 and 45, I can see that 24 and 45 have a common factor of 3. So let's divide by 3. And 24 divided by 3 is 8, and 45 divided by 3 is 15. Now 8 and 15 do not share any common factors, so 8/15 is our final fully simplified fraction. You may have also spotted here that to get from 48 90ths straight to 8/15, you could have divided by 6. For our next question, we are using an algebraic method to write 0.258 recurring as a fraction. And this question is similar to the last one because it is just part of the decimal that recurs, not the whole thing. But we're still going to approach in a similar way. So we start off by letting x equal 0.258 recurring. And if we wanted to write this out a little more fully, it's just the 5 and the 8 that recur, so this would be 0.2585858 and so on. Now we multiply by 10, so x multiplied by 10 is 10x, and 0.258 recurring multiplied by 10, the digits shift to the left to give us 2.5858 and so on. Now I'm going to use a little trick to try and save us a little bit of time here. I can see that if we multiply this decimal by 10 again, we're going to end up with 0.85 recurring after the point. This doesn't match the decimal we've got currently, and it doesn't match the decimal before either. However, I can see if we multiply by 100, that this decimal will shift up 2 places to the left and will also end in 58 recurring. We will then have 2 decimals that look identical after the point that we can subtract to eliminate the decimal. So let's multiply by 100. So 10x multiplied by 100 is 1000x. And multiplying the decimal by 100 shifts it to the left 2 times, which gives us 258.5858 and so on. We now have our two decimals that look identical after the point because they both end in 5/8 recurring. So we're going to subtract these two decimals. If you wrote out 100x in the middle of these two steps, you would still obtain the exact same answer. So we are subtracting 10x from 1000x. So 1000x subtract 10x leaves us 990x. And then subtracting the decimals, the recurring part cancels and we are left with 258 subtract 2, which is 256. Now to solve this equation, we divide by 990. So we end up with x on the left and 256 over 990 on the right. So our fraction is 256 over 990. Now this fraction does actually simplify and we could choose to write this as 128 over 495 if we were to divide numerator and denominator by 2. However, since the question doesn't ask us to simplify, either answer is perfectly acceptable. Now you've seen a couple of questions where only part of the decimal recurs, you might want to have a go at converting decimals like this into fractions for yourself. If so, pause the video now, have a go and press play when you're ready to see some solutions. If you paused, welcome back, let's have a look at some solutions. So for our first question, we are going to let x equal 0.45 recurring, and if we write this out in full, just the 5 part recurs, so that looks like 0.4555 and so on. We then multiply by 10 to give us 10x, and shifting the decimal over to the left just once gives us 4.5 recurring. We need two decimals that look identical after the point, and I can see if we multiply by 10 again, we're going to get exactly this. So multiplying 10x by 10 gives us 100x, and shifting the decimal to the left just once gives us 45.5 recurring. Now we have two decimals that match perfectly after the point, so it's these two decimals that we're going to subtract. Then subtracting 10x from 100x gives us 90x, and when we subtract the decimal part, the 0.5 recurring cancels and we're left with 45 subtract 4, which is 41. Now to solve our equation of 90x equals 41, we divide by 90 and we end up with x on the left and 41 over 90 as our fraction, which is our final answer. For our second question, we have 0.284 recurring to convert to a fraction. So we start off by letting x equal 0.284 recurring. And if we write this out a little more fully, we could write it as 0.28484 and so on. Now let's multiply by 10. So we have x multiplied by 10 is 10x, and if we multiply the decimal by 10, the digits shift to the left one place to give us 2.84 recurring. Now if we want to make this method a little shorter for ourselves, I can see that if we multiply this decimal by 10, everything will shift to the left one place and we will end up with a decimal that starts 4848, which doesn't match either of the decimals that we currently have. However, if we multiply by 100, the decimal will shift 2 places to the left and the decimal will end 8484, which matches this decimal that we have here. So let's do that. Let's multiply by 100. So 10x multiplied by 100 is 1000x. And multiplying the decimal by 100, we said shifts to the left 2 places. So we get 284.84 recurring. Now we have our two decimals that match perfectly after the point. We're going to subtract. So subtracting 10x from 1000x gives us 990x, and then subtracting the decimals, we can see that the recurring part would cancel completely, and we're left with 284 subtract 2, which is 282. Then solving the equation that we're left with by dividing by 990 would give us x on the left and 282 over 990 on the right, which is our final answer. This question doesn't ask you to, but this second fraction does in fact simplify to 47 over 165 if you were to divide numerator and denominator by 6. Either answer is perfectly acceptable. Now for our final kind of question in this video, we're going to look at proving a false statement. So this question says we have to prove using algebra that 0.4 recurring subtract 0.14 recurring equals 10 over 33. In order to prove that this statement's true, we're going to begin by actually pretending we don't know the answer to 0.4 recurring subtract 0.14 recurring. We're then going to work out the answer, and we're going to show that whatever we get is 10 over 33. Given that the answer we have in the question is a fraction, it's going to be helpful to convert these recurring decimals into fractions also, and we already know how to do that. So let's begin by converting 0.4 recurring into a fraction. So we'll do this by letting x equal 0.4 recurring, or 0.444 and so on. We then multiply by 10, x multiplied by 10 is 10x, and 0.4 recurring multiplied by 10 is 4.4 recurring. We have two decimals that match perfectly after the point here, so we subtract x from 10x. So starting with 10x subtract x, we get 9x. And then subtracting the decimals, we can see the recurring part would cancel, and we're left with 4 subtract 0, which is 4. Then solving our equation by dividing by 9, we get that x equals 4 over 9. So we have converted 0.4 recurring into a fraction. Just a reminder that even if you knew that 0.4 recurring was equal to 4/9, the question specifies that we have to prove using algebra, so this method is essential. Now we're going to use the exact same method to convert 0.14 recurring into a fraction. And since we've already used the letter x, this time I'm actually going to let y equal 0.14 recurring. And so we end up with y equals 0. And since the dot is above the 1 and the 4, both digits repeat. Now we want a decimal that matches this completely after the decimal point. I can see that if we multiply this decimal by 10, we will end up with a decimal that starts with 0.41 instead of 0.14. However, if we multiply by 100, the decimal will shift to the left 2 places, and we'll end up with another decimal that begins 0.14. So let's do that. So y multiplied by 100 is 100y. And multiplying the decimal by 100, we shift to the left 2 places to give us 14.1414 and so on. Now we're going to subtract because these two decimals match completely after the decimal point. So starting off, we have 100y subtract y, which is 99y. And then subtracting the decimals, we can see that the recurring part will cancel, and then 14 subtract 0 is just 14. We're left with 99y equals 14, so dividing by 99 gives us that y equals 14 over 99. We have now successfully converted both of our recurring decimals into fractions. Now looking at what we were originally trying to prove, we were actually trying to work out 0.4 recurring subtract 0.14 recurring. We now know what each of these decimals looks like as a fraction, so let's rewrite this question. Instead of 0.4 recurring, we can write 4/9, and instead of 0.14 recurring, we can write 14/99. Now we need to subtract the second fraction from the first. Let's get a common denominator. I can see that 9 and 99 have a common multiple of 99. If we're going to make the first fraction have a denominator of 99, we're going to need to multiply by 11, and 4 multiplied by 11 gives us a numerator of 44. And the second fraction already has a denominator of 99, so we don't need to do anything to it. And then subtracting 14/99 from 44/99, 44 subtract 14 gives us 30, so we have 30/99. And our fraction of 30/99 has a common factor, numerator and denominator, of 3. So dividing by 3 gives us 10 on the numerator and 33 on the denominator. So we have proved that 0.4 recurring subtract 0.14 recurring is in fact equal to 10/33. Here's another similar type of question, so if you would like to check your knowledge and have a go, pause the video and come back when you're ready to see the solution. If you pause the video, welcome back. Let's have a look at a solution. So similar to the previous question, we're going to start off by pretending we don't actually know the answer to this addition. We're then going to work out the answer to the addition, and our answer should be equivalent to 53/66. In order to obtain an answer that's a fraction, it's going to be helpful first to convert the two decimals to fractions. So starting off with 0.63 recurring, we let x equal 0.63 recurring, or x equal 0.6363, and so on. In order to find a decimal that has the exact same pattern after the decimal point, we need to multiply by 100 and shift this decimal 2 places to the left. So x multiplied by 100 is 100x, and 0.63 recurring multiplied by 100, we shift 2 places to the left to give us 63.63 recurring. Now these two decimals match perfectly after the decimal point, so we're going to subtract. And 100x subtract x is 99x. Then subtracting the decimals, the recurring part will cancel, and 63 subtract 0 gives us 63. Then solving our equation of 99x equals 63, we can divide by 99 to give us x equals 63/99. And looking at this fraction, I can see that 9 is a factor of 63 and 99. So let's simplify this fraction a little bit, and we can write it as 7/11. This will make it a little bit easier to find a common denominator later on. Now we've converted 0.63 recurring into a fraction, let's do the same for 0.16 recurring. Since we've already used the letter x, I'm going to use the letter y this time, and we are going to let y equal 0.16 recurring, and if we write this out a little more fully, we can write this as 0.1666, and so on. Now let's multiply by 10 so that we just have the recurring part after the point. So y multiplied by 10 is 10y, and multiplying the decimal shifts to the left 1 place to give us 1.6 recurring. Then I can see if we multiply by 10 again, we'll end up with another decimal that starts with 0.6 recurring, so let's do that. So 10y multiplied by 10 is 100y, and multiplying the decimal by 10 we'll shift over to the left, so we'll get 16.6 recurring. And we have our two matching decimals after the point, so we're going to subtract 10y from 100y. So now subtracting 10y from 100y leaves us 90y, and then subtracting the decimals, we can see that the recurring part would cancel, and then 16 subtract 1 is 15. So we have 90y equals 15, which we can solve by dividing by 90, which should leave us with y equals 15 over 90. And 15 is a factor of 15 and 90. So dividing by 15 on the numerator and denominator should give us 1/6. Again, this step should just make it a little bit easier for in a moment when we find a common denominator. So now going back to the original question, we have converted both of our recurring decimals into fractions. So our original question of 0.63 recurring add 0.16 recurring, we can now rewrite as fractions. So 0.63 recurring, we converted to 7/11ths, and 0.16 recurring, we converted to a sixth. Now we need to add the two fractions together. So a multiple of 11 and 6 that we could use is 66. So let's get a common denominator of 66. And to give us a denominator of 66 on the first fraction, we multiply by 6, and 7 times 6 is 42. And on the second fraction, to get a denominator of 66, we multiply by 11. So 1 multiplied by 11 gives us a numerator of 11. And then 42/66 add 11/66. 42 add 11 makes 53. So we end up with 53/66, which is what we were trying to prove back in the question. And that's our full proof complete. Thank you so much for watching this Now Maths video. Please make sure to like and subscribe if this was helpful, and hopefully we'll see you soon.